Hi everyone, today we're going to talk about how to delineate a watershed in QGIS using digital elevation model data. So the way that we do this, you can get the data from the USGS a couple different ways. I'm going to show you both of them. First, the national map. If you search for the national map, you'll come to this landing page. Uh, Even though there are a couple of pieces on here that say download data, I've found the easiest way to get to the interactive download data section is to click on this national map tool and then to actually click on data download, which will bring you to this screen here. So let me just point out a couple of features of this screen because it does have a lot of very useful data links. The classic USGS topographic maps, the historic, and the new ones. I find the new ones are maybe a little busy, so I usually get the historic ones, but they are all available for download basically as images there. We're going to talk specifically about elevation in just a moment, but let me show you just some of these other data packages available. So boundaries as a shape file. You can download the National Hydrography dataset in its entirety as a geodatabase. And that has actually a whole lot of information on it, including the watershed boundary dataset. Imagery, map indices, names of places, structures, the topography, the actual contour lines used on maps. In some places, you can find the bathymetry of places throughout the U.S., transportation, and the vegetation cover colors on the classic topographic maps are also available. So let's go up here, and again, let me save what we're actually going to download this for just a second. You can get LiDAR data. You can get LiDAR from most of the country, but third arcsecond DEM, or digital elevation model, is really good. So that's actually what we're going to use as the third second. You can go higher resolution if you wish. One thing I'm actually doing a little bit out of order up here is where you will determine, okay, what area do we want? And we're gonna do Little Pine Creek again, the area that we did with the flood return periods. And worked some of the data from Little Pine Creek. The gauge is right down here. But we're going to take a look at the entire watershed. Now, there are a couple ways to search. Extent is a rectangle that you click and then drag out an area you want to look at. And we do need the entire watershed. So here, where we see Pine Creek come over here and Laurie's Run over here, we know that the Little Pine Creek watershed is not going to go any further past that. So that's why we can stop right there. And so this is a pretty good extent. If you have something a little bit more irregularly shaped, you can do a polygon. If you just want to see what is around a particular point, you can use a point or enter the coordinates yourself. Now that we have the data set selected and an area of interest selected, we can do a search, and you'll see that we get, you can actually see a thumbnail of the two data sets You'll notice immediately that they're different. They look different shades, and that's because of the significant elevation here is causing there to be less of gradation here. We don't have as wide of a range of elevations on the one on the left. So when we get this into QGIS and merge the two together, it will come out and it'll look pretty. It'll look completely seamless. So we want to download those. Download the TIFF file here. Download the TIFF file here. And I've already downloaded those and moved those over. I wanted to show you another tool to download data because National Map really is intended for the United States. So when you work outside of the United States, it is, I found, a little more convenient to work with this site, Earth Explorer. It is earthexplorer.usgs.gov. And unlike National Map, you do have to sign in. It's a free account. These are all federally funded data sets that are free for you to use. And similarly, you enter a bounding box. You can use the map. If you click on Use Map, it just uses the extent of what you're zoomed into at the time. If you do use the map, you can then move the corners around. Or, of course, you can type this in yourself. Data sets. Now, for US Map, that's great, or National Map, that you don't need to worry too much about some of these global data sets. But when you are working outside of the US, I have found that the shuttle radar topography mission is usually the easiest to use, and there's a 1-second global product there. Non-void filled and void filled, you actually will be doing the void filling ourselves in QGIS, so you don't have to worry about that right now. And of course, when you click on results, you also get a footprint, and you can download these. Now, the difference here is you do have 3 different options, and this is what I wanted to show you here. GeoTIFF is what we got from the National Map, but these BIL files, which are significantly smaller, I've found to work just fine. So when you've downloaded your data, you want to open up QGIS. If you're just opening it for the first time, then you'll need to open a new project or an untitled project. I forget exactly what it says. It's usually on the lower left. And you can then start dragging in your data. So as I mentioned, these are the two data files that we got. And here we're given the default options to convert to the project CRS, or coordinate reference system, and we're going to actually transform these data later. So we're going to accept the defaults here. This is just for visualizing the data. This does not actually transform the data at this step. It's a little hard to read on my screen, but the one on the left only goes up to 464, and the one on the right goes up to 896. It's not too big of a deal because when we go up here to roster, what we're going to do is we are going to merge. And we see here, that we want to select both of the input layers. And we're going to actually save to File. And because we've been doing this in this folder here, I'm going to say merged TIFF. Okay, and we run. I don't think I mentioned this before, but one of the things I like to do is make sure that all of my data are within a single folder. And then even after that, every, let's say, every shapefile, as you may have encountered in previous classes, shapefiles are actually at a minimum 3 files. While we're waiting for that to finish up, let's go over to Stream Stats and let's do a comparison here so that we know. Oh, it won't let me pick the won't let me pick the actual cell. I'm going to get as close to the gauging station itself as possible. And it has completed in QGIS. So this is on top of it. We can look just at this. And what a lot of people like to do is to colorize this slightly differently. And we can see here all of the elevation. So from here, we can zoom in and actually just start getting our DEM. I do want to show you the National Hydrography dataset. It comes in as a geodatabase, so the way you handle this is you drag the entire folder in. And it asks what you want to add. And I'm just going to add a few of these area lines. And then, of course, you need the watershed. Data file to do the catchments. So let me add those 3. Oh, yeah. So we are has this nice topo blue as one of the standard colors. Sometimes it's still filling in. sometimes what I'll do is I will change, whoops, not that. I'll change the outline of the area to be no pen, because that way sometimes the outside actually gets kind of covered up by the outline. I'm sorry, the blue gets covered up by the outline. I'll do the same thing here, just for consistency. Oh my, that's not what I meant to do. And StreamStats has finished. I'm going to download the basin. So that's downloaded. And we're also going to continue so that we can get some of the statistics. Let's take a look at the peak flow, and we can also see how we did compared to last year, or last time we played with this watershed. So here, 5.7 square miles. Of course, we will definitely have to convert that to something more useful. But let's save the report here so that we can take a look at it in comparison. Actually. And we'll go back to QGIS. What we're going to do is find the point of our outflow. And we do need to figure out what our point is. Having a lot of trouble zooming here. Actually, that gives us the latitude and longitude, although I was going to pull from the gauge itself. There's the latitude and longitude. The easiest way, usually, to get a point into QGIS, and to save it in a very simple way, I think, is just to save the point data. And the way I usually do this is to just create a text file and to insert those coordinates. You can also do this by creating an Excel spreadsheet and adding the coordinates, and then saving as a CSV file. But what I'm going to do is I'm just going to add a text file. I'm going to call this station.csv, and I'm going to enter in X and Y, and for X I'm going to put in 93811, and for Y I'm going to put in 40.52035, and just make sure that those are the same. They appear to be. And Save that. And we can add those, add that to our map by going under Layer, Add Delimited Text Layer. You select your file, and you select your X and your Y coordinates, your coordinate system, and it even gives you your sample data. And we add that and close that, and there it is, our station location right there. So now that that's loaded and our point is loaded, oh, I should point out there are other ways to add a point. You can even select points. If you go to create layer, create a shapefile layer, make that layer editable, and then you can add in, that's the shortcut to it, but once you make it editable, you can add point features from that. And here we are with our merged TIFF file. What we want to do here is reproject this into the relevant UTM, which is to say a flat projection. So the way we do that is go under Raster, Projections, Warp, and what we want to do is a target CRS. I'm going to use the CRS tool here, and it is one of the one, there we go, 17. It's one that I use, but not frequently enough for it to be in the frequently used. So we use UTM zone 17N. UTM stands for Universal Transverse Mercator, and 17 is the zone. North just refers to it's in the northern hemisphere, although UTM conventionally it goes all the way up and down, but the coordinate reference systems do identify between between north, and for instance this one 36 south is in eastern South Africa. So we're going to reproject to UTM 17N. We're going to run that, and it reprojects. And close. So now we can save this, export save as. Should have done this in the other. Let's see here. We're still in the DEM. I think I was calling this let's call that merged 17N, just to keep track of what it is. Add that. And just to keep things clear, And so merge 17. And the next thing we need to do is fill the voids. Now, voids are areas that could cause discontinuity in the streams or discontinuity in the upstream areas. So this is something like a depression, and we need to fill in those so that it does not hang up the algorithm later on. We're going to go to the processing toolbox. We're going to look for fill sinks. There are a number of fill sinks options, but the Wang and Liu is the most popular. Merged. Do want to make sure that the slope is set to 0.01. And then we also want to uncheck the flow directions and the watershed basins at this time. And temporary file actually should be... Actually, no, I'll save it to a file here. And run. And now that the fill sinks is complete, what we are looking for now is we want to find the stream order. Now, recall from class, Strahler order is the most popular ordering or numbering system, and we are going to save it to temporary file this time because we're going to convert this immediately following it. But we're going to put in the DEM filled and run this. And with the Strahler order determined, it's right here. This is a temporary layer, so we have to be careful. But what we see here is all of the flow paths that would be followed, and they are determined by order. And Strahler number, recall, is actually we're going to use that next. Strahler number, recall, starts at 1. So all of these black areas, actually 1 through 12. So all of these areas begin at 1. Those would be the highest up and the least amount of slope. Coming down 2, 3, 2, 8. Oof. All right. Let's see, what's this? 5. So we get quite a bit here. 5. Let's see. Probably, yeah. And what we're doing is we're not just clicking around. We're actually looking at, okay, what are the Strahler number values that we want to use. And now that we have this analysis, what we're going to do is, oops, there we go. We're going to go to the roster calculator under the roster menu. And what we want to look at is this Strahler order. And we want to effectively filter our results to be greater than or equal to 5. And what we're going to do is save that as Strahler 5. Incidentally, this is the second time I've done this. I wanted to point out, because a lot of the documentation on the Saga say that it can work on latitude and longitude projected CRS, and it doesn't. It failed miserably. Actually, in a very frustrating manner, it failed. So do make sure you export, or reproject to UTM. So we're going to keep this in UTM and export that. All right, with that complete, get rid of this. So we have ones and zeros. We also have some no data that I'm hoping is not going to cause problems. Our point of delineation is not actually on the stream. So what we need to do is put the project, up until now it hasn't really mattered, we need to put the project into the coordinate reference system that we've been using. And again, this is just for for display. What this does is it changes what's happening down below here. It's now giving us coordinates in our preferred coordinate reference system. So what we're going to do is make sure the cursor is on there, switch over, and just type those coordinates in. 589964.8 and 4486.064. And these are all in meters. So I'm actually going to change that just to a 5. And we'll save that. And we can once add layer, delimited text layer. And usually when it's, there we go. Usually it defaults back to the project. Okay. And add and close. And there it is. And we can make that a 4. And zoom in. So now that we have the station information, we have the Strahler number. What we're going to look for is upslope area and target area. Here we go. Target X, we can once again just pull this out of our file information. So we're putting in the X and the Y coordinates. The elevation, in this case, we want that to be our filled DEM, which, here we go, specify a method, deterministic 8. And we definitely want to save this to a file. Watershed. And run. Now that the upslope area has been computed, we see here the watershed has been delineated. There's one final step. It is still currently as a raster file, so we want to make this into a vector file. So we go under the raster menu once again, and we want to polygonize. So raster to vector. And the input layer is watershed. The band number, this would be if, for instance, color images frequently are in RGB, red, green, and blue. So it would contain multiple bands. However, this is a simple mask layer, and it just contains one layer. Name a field to create. It's only creating one field, so it doesn't really matter. But this would be our final shapefile, watershed .shp. And that's it. We run that. And this typically does depend on the size and complexity of the shape, how long it will take to actually run. That went pretty well. Now it still looks like a big filled in blob, but remember, we can double click or right click and go to properties, go under symbology on the left, and change this from a simple fill. We can do simple line. You could do any number of things. You can also do a simple fill with a transparent interior. That's another kind of workaround. We're gonna do, 1 millimeter wide line. It's going to be solid. Yeah. And there it is. There's our watershed. Now, we previously had downloaded StreamStats watershed coming out of this red dot, which is nearly the same place. Remember, we just had to move it over because of we wanted to make sure we were right on one of the rivers as identified. Whoops. What do I want to get rid of? This and this. Maybe put our nice colored one back on. And we see here the watershed. But to compare it to the StreamStats watershed, we activate this, and we see that the two watersheds are almost identical. There are going to be a couple of differences. The StreamStats database uses a slightly different DEM, may even use that 1/9 arcsecond DEM. The algorithms are almost certainly a little bit different. But if you zoom into this area here, which appears to be one of the areas where there is actually a difference that we can see, we can examine our DEM and see here that at least the DEM that we used seems to put some pretty high peaks along the line that was determined by our algorithm. And now that we have the watershed delineated, we want to find the area of the watershed. If we right-click on the watershed layer itself, open the attribute table, we'll see just the identifier here. What we want to look for is the field calculator. When we open that, we get a new field. We can create the field area. We want it to be a whole number. And this is just the length and precision. So, oh, I'm sorry, not whole number, decimal number. The length of the field, the number of numbers, and the number of decimal places here. Then these are all of the options that are available. And there are a whole lot. Area is one of those that is easy to remember. It is $area. Just for the record, other ones that I find easy to remember are $X and $Y, which will give you the X and Y coordinates in whatever coordinate reference system that you're looking at. But this here, I already am seeing the preview, because of course there's only one element in this layer. When I click yes, whoop, this is giving me a value of 14,929,236 point something. So I could have gone with a whole number. This is the area. Remember, we changed it to UTM. UTM, the units on UTM are meters. So this is in square meters. This is 14.9 million square meters. .9 square meters. If we, and we'll close editing on that, and we'll want to save changes, and that'll save it in that shapefile. The StreamStats watershed, I'm going to do the exact same thing here, but we can look up the StreamStats watershed as well, because $14,881,000. Oh, also, if you want to display it in something else, you can change it. Actually, that's easier. So because it's square kilometers, or I'm going to convert it to square kilometers, it would be 1,000 times 1,000. So e to the 6. Actually, I'm not going to save it that way because I want to save it in the same way as the other one. You can toggle the editing mode here as well and save. So that was 14.8 for StreamStats that we measured, and then 14.9 for what we delineated. If we go over here, it's 5.75 square miles. If we convert that here, 14.89. I think in stream stats we measured 14.88, and then hours we measured 14.9. So pretty good.